Thank you, Nancy, for the introduction. And thanks to all of you for choosing to spend the next half hour listening to my talk. So let's get started. I hope that you will agree with me that today we can get our hands on very interesting robotic devices. They are much more robust, much more integrated, much more efficient than they used to be. And we also see the development of new devices here on the right that definitely will extend the range of applications that we can consider. If you looked at the webpage of this conference, you may have noticed that motion and path planning was the second most, let's say, as it's put here, leading research area in the field, judged by the number of papers. This conference got 107 papers on motion and path planning. Versions of this problem, which underscores the importance of the topic for robotics. Actually, motion planning did not start in robotics. The problem is very well defined, and it was defined in the 80s, mainly by people who were doing theoretical work. So you had a model of the world, you had a model of the robot, and you wanted to solve the motion planning problem, getting from a start to goal without collisions and respecting all the robot constraints. So many of us have seen various versions of this problem. The people who did algorithms and the people who did computational geometry who started looking at this problem in the 80s looked at the various simplest versions of the problem, and look at the right side, the complexity column. The results were totally disappointing. P-space complete, NP hard, undecidable. Fortunately, roboticists persisted on this, and today somebody who wants to work on motion planning has an array of techniques in their disposal for doing motion planning. It's really impossible to have a taxonomy of motion planning approaches in one page, but nevertheless, I want to mention that clearly anyone who's doing motion planning today has in their disposal sampling-based motion planning techniques like PRM, RRT, EST, heuristic discrete search methods like the Starlight, optimization-based approaches who actually took advantage of some of them advances in convex optimization and gave us very interesting algorithms, and definitely control theoretic approaches. Myself, I have been working a lot with sampling-based planning for many years, and to remind some of you of the audience, but I will not stay long on that, these are the techniques that somehow, the PRM-like techniques, somehow sample the configuration space of the robot and find free samples in that space, and somehow connect these samples, it doesn't have to be by a straight line, and find a roadmap in that space, and then the idea is that you use this roadmap as a set of highways to go from one place to another. You get to the set of highways, you get as close to the goal as possible, and then you depart to get to your goal. These techniques found a lot of applications. Also, tree-like planners have been extremely successful. Again, sampling-based planners, somehow, and there are many versions of these planners, they expand the tree from the start configuration of the robot in the configuration space of the robot, and they grow this tree until it gets to the goal. And once you get to the goal, you are done. A big advantage of these planners is that they can deal with systems with kinodynamic constraints because they integrate forward the motion constraints of the problem, of the system, and they don't have to solve a two-point boundary value problem. As the field matured, we have witnessed a plethora of techniques that are a variation of sampling-based methods. I used to keep tracking of that, but I stopped around 2014 because it was impossible to keep things in a slide, and it was meaningless to put down all these planners without having time to explain them. But what I get from this is, first, that the problem that we were trying to solve in practice was rather an easy problem. That's why we were successful with all of these techniques. We didn't try to apply these planners to pathological problems. In practice, they do very well. The second thing is that the initial ideas of trees or roadmaps were very, very general. And they were developed without any consideration of the robot that you had in mind, or the environment in which this robot was going to move. So once you get to a particular type of robot, or to a particular environment, yes, there are many, many adaptations that you can do to these planners to make them more efficient. So people learned difficult parts of the configuration space and guided the sampling, or learned things about the workspace and used the workspace information to guide the sampling. We had discussions about importance sampling and many, many other ideas that make these planners efficient in practice, and there are lots of variations of these planners. There are some difficulties in this, that remain with many of these planners. One of them was the quality of paths, right? The paths that you get out most of the times out of sampling-based planners don't look good. They're not the kind of plans that you want to use on the robot. You have to use some kind of a smoothing technique to make them look well. But it was really, I think, a big advance when Karaman and Frazzoli showed that you can get sampling-based planning to be asymptotically optimal. It was a great result. In theory, you have to decide if you want to use such a planner or not. In theory, it was a great result. In practice, you have to trade the performance of these planners with the kind of results that you get. And these results were for planners that did not have kinodynamic constraints, but Kostas Bekris and others later extended these results to asymptotically near optimal kinodynamic planning. So in theory, we are doing well, and in practice, we are doing well with these planners. I have been surprised over the years at things that were not solved. For example, one of the topics that my lab has been working on was planning with constraints. And we work with NASA, we work with a fairly complex robot, the Robonaut 2, and we had to plan motions for this robot. We had a lot of constraints to obey. The torso had to be upright, the feet could not be too far apart, the hands had to maintain a certain distance if this robot was holding something, because the purpose of this robot is to be on the space station, and you cannot just let things go. We looked at the field. There have been some approaches that had excellent ideas on how to deal with constraints, but mostly what was done is that the authors would choose some well-performing sampling-based planner and then would augment this planner to take account of the constraints. My student, Zach Kingston, recently came up with a very nice idea. What he did is that he pushed the satisfaction of the constraints from the planner to the space itself. In this way, decoupling the sampling strategy from the satisfaction of the constraints. So this gives you the option to use the best planner for your particular task and to still have satisfaction of constraints. And this can be done by endowing the space with projection operations, and we understand now that we can project a point to a constraint manifold, with gradient descent, for example, using the pseudo-inverse of the Jacobian of the constraint function. And we also understand how to compute a discrete geodesic, that is to interpolate, always satisfying the constraint. So we have been able to use different sampling-based planners underneath, and at the same time, with this recent work, turn valves and slide doors open and try to make this robot a useful robot in the space station. It is something that I would like to point to your attention, if you don't know it, that we do support an open source motion library, which is called Ompl. And this has been an effort not only of my lab, but of several other labs that have contributed planners, and it's an open source library, as I said. It is very active. If you want to do motion planning today, I would encourage you to have a look at this library. It contains many sampling-based planners developed by us and by others, but also we see contributions for non-sampling-based planners now. It is a good idea to look at these planners. Many registered users, many downloads, and Mark Moll has been maintaining this library for many years. It is good to use this library because clearly with motion planning, there is no best planner. It depends on what is the task that you have at hand. And this, for example, on the left, you can see benchmarking of different planners against a set of benchmarks. It can give you an idea of which planner tends to perform well. On the top right, if you are using an optimizing planner, what is the convergence rate, and so on and so forth. It is important to understand these things once you put your planner on a real robot, and this library connects with ROS and MOVEit. We are trying to push our results to the community to the extent possible, so very soon this library will have all the capabilities for planning with constraints. Here is an example of what you can do in a fraction of a second, 168 degrees of freedom, 69 constraints. We are also interested in going beyond motion planning, and this is planning that would satisfy different goal specifications. So here I'm giving you an example that is also a segue to the second part of my talk. You have a space and you have a robot in here, and you wanted to, and you have a goal specification, but the goal specification is the following. In the future, visit region P1, P1 is at the very top of the slide, and then visit region P2 or visit region P3. This can be expressed in some logic. In here we use linear temporal logic. How do you plan for a mission like this? I call this moving beyond the reach the destination paradigm, doing a mission. And here is an example from work in our lab. You can see an initial configuration of these three cans. The goal specification is that we want them in the tray, and then we want to push the tray. We do not instruct the robot which can to pick up first and which can to pick up second. This is done done automatically from the high-level specification to the low-level motor control. I call this task and motion planning, and I think it's a challenge for us as a community. In general, if you see this problem from far away, you have a task, a complex specification that you want to satisfy. You have a robot and you have an environment model. Task planning means that you have to decide about a sequence of discrete things. Do this first, do that next, and so on, until you get your goal, your whole task done. Motion planning, however, is continuous. You have to find the motions to perform each of these tasks. And although we know how to deal with each of these different topics separately, that is task planning and motion planning, the combination of the two in our work turned out to be pretty challenging. It turned out to be pretty challenging to get a plan or a policy. It's not only us who have been working on this problem. I think this is a problem that has been looked by many, and it is considered a challenge at this point. We have, in the lab, worked on it as a framework called the Synergistic Framework for about 8 years. Erion Plakou, Amit Bhatia, Morteza Lahijanian, and Kilian He have done contributions in this, and this is how it goes. You have some kind of specification in a formal language. Here we use CoSafe LTL, but it doesn't really matter. You have an abstraction of the space and the robot, and you find tasks by doing weighted graph search. You find motions by doing sampling-based motion planning, and there is a back and forth going between the two. How do you get this weighted graph? This can be tricky. If you have your goal as some kind of specification, then in a, let's say, a high-level logic language, you can get from CoSafe LTL, for example, we could get non-deterministic finite automata that told us exactly how to specify a task. So if we followed these arrows and we got to a goal state, we knew that we had satisfied our task. Then we have to come up with some kind of abstraction of the space. Maybe, you know, neighboring regions from where to where you can move. And if you take the cost product, you are ending up with a graph, initially the same weights in this graph. But once you start executing the motions that are specified by this graph, then you can use a sampling-based motion planner to gather information about how difficult the task is and use this motion planning difficulty to weight back the graph that I showed you before. By doing that and by repeating the loop many, many times, we were successful in solving pretty challenging problems that had to do with task and motion planning. But it was extremely important to get the models right, to have task plans, to try to implement them, and to give some feedback back to the task planner to help this planner give us tasks that are more likely to be executed in practice. Neil Dentham did a constraint-based approach for the same problem. Again, the idea is that you have the task, you have the planning domain, but you encode everything as a constraint, and you use an incremental solver, a satisfiability solver, to satisfy the constraints. Let me explain this to you. the sampling was done again using motion planning. So the idea here is that the task is written as a constraint. You describe the start state, you describe all the in-between states and the goal condition as a Boolean formula, and then you use a big tool like a SAT solver or an SMT solver to find an assignment of states at each step of the plan. Here's an example where we have a valid assignment, but then you're going to check with a motion planner, and if a motion is infeasible, then you add a constraint actually describing the infeasible plan, and you ask the incremental, you use the incremental nature of the solvers to find another set of tasks that can execute the global mission that you're interested in, and you continue doing that until you validate with motion plans and you have a task that executes what you would like to do. And we have found that by using modern tools like SMT solvers, we can have significant speed up versus solving from scratch this problem all the time. So now, all this work was done for controlled environments, but as I'm sure we all agree, much of the interesting work to be done is in environments that are uncontrolled. And here, for example, I'm talking about environments that are partially unknown. I'm talking about environments where you may have another agent interacting with a robot and maybe interfering with the task that you would like to execute. I'm talking about environments where you have action uncertainty and sensing uncertainty. So I will talk about a few things that we've done in our laboratory in an effort to stimulate interest in these problems and motivate some of you to work in related areas. Partially unknown environments and task and motion planning. Work done by Moteza Lahijanian. So suppose you had a specification, you had your janitor robot, you wanted this robot to water the plant, to clean the blackboard, to turn off the coffee maker, to pick up the vacuum cleaner from the supply room and vacuum the orange room. Everything is fine, you know how to solve this problem, but suppose this robot goes around and some doors are closed. Then what do? Do you give up? It is interesting to understand what does it mean to have partial satisfaction in a physical environment. It is not a topic that has been dealt with a lot. I think lots need to be done. For a satisfiable problem, as I told you before, we understand how to satisfy the task. We understand what is happening with the abstraction of the environment. We can have a model and a graph that tells us how to go about finishing a task. But when things change in the environment, things break in our abstraction, and they break in the final graph that we are to search. So here comes the interesting part. How can you still solve the problem? One idea is to search and to end up in a way that you end up in the closest state to your final state had all these edges not been removed. In this case, that would mean for this particular robot that you are going to see that the door is closed, you are not going to water the plant, but you are going to do the blackboard, and you are going to the coffee maker, but since the utility room was closed, the supply room was closed, and you didn't pick up the vacuum cleaner, you are not going to go and clean the desk. So I think we get to very interesting notions of what is partial satisfaction, and I'm just showing you one thing here. Lots to be done. Let's look at action uncertainty and the task and motion planning problem. When we have action uncertainty, we all know that we are going to deviate from a path. And when you have a task to complete, then you want to increase your chances of completing the task, given your action uncertainty. Again, a problem that has been looked at by various people. What we did is that we partitioned the space, we defined local MDPs to bound the transition probability from one region of the space to another region. We put it all together and found an MDP that has bounded transition probabilities. And then what we did is that we used our task automaton, as I said before, the bounded MDP, and we created a product MDP that can be solved with, let's say, standard methods like value iteration to understand what are the policies that will maximize the probability of success of a task. And very, very briefly, and there's, let me add uncertainty to this task and motion planning problem. Here we have a robot that wants to fetch the green objects, let's say, from the black shelf, but there are these tables around and the robot has certain actions and imperfect perception, so it doesn't know exactly where these tables are. And of course it can be modeled as a POMDP, the whole problem. I understand that. But we found that sometimes tweaking the problem, that is not trying to maximize rewards as is typically done in POMDPs, but having a Boolean objective that says the robot always should be safe and should reach the destination, allows us to contain the problem. The insight here is that not every plan can satisfy the Boolean objective, so compute reachable beliefs only on the satisfiable plans. We have found how to do that, nice representations and quick solutions. And I will finish by discussing another problem where you have a human in this environment. You have your task and motion plan, for example, for your robot to stack all these cups. But a human is around, and the human may interfere with your actions, and you have a bounded energy, of course, in your robot. And then the problem changes again. We are talking about synthesis, reactive synthesis in this case, that can be modeled as the game. So the abstraction of your space become the game rules, the task becomes the winning condition, and the policy that guarantees task completions is the strategy that guarantees that the robot wins. So I see that there are very, very interesting connections when you try to put things together. You want to use different planners, you want to be able, in an easy way, specify tasks, you want to be able to interchange components. This is an example from our work with NASA. This robot executes, which is actually up in the space station, executes different tasks and aspires to be an assistant to the astronauts. But putting it all together, I hope I have convinced you that it creates a lot of challenges. Motion planning used to be the core of what we were doing. I think task and motion planning is what we should be looking at today. It's a much richer problem. It allows us to meaningfully connect with formal methods, for example, if you have a partially unknown environment, to connect with what is happening with MDPs, if you have action uncertainty, POMDPs, if you have sensing uncertainty, games, if you have an uncontrollable agent in the environment that can model a human. And by looking at this problem together, I think we can switch a little bit the way we've been thinking about solving parts of the problem and try to solve more meaningful, let's say, components that we will later put together, and maybe rethink the role of learning in this kind of problem. So I'm going to stop here. I want to thank the people who have participated in this work, our funding sources, and also thank all of you for your attention. Thank you very much.
Thank you for the talk. This is very interesting. I'm wondering, from your point of view, how does deep learning and machine learning play in that big picture of yours that includes task and motion planning and all other uncertainties?
I cannot fully answer the question because honestly I don't understand this question very well. But I think that it is it is a better, let's say, framework to look at the learning, not only deep learning, but learning more generally in the context of task and motion planning than in the motion planning problem by itself. I think this question, we need to wait a little bit before we can answer it.
Thank you.
Okay, so converting an LTL formula to an automata, right, that takes exponential time. Actually, it's polynomial space, right? So does that slow down your process Like, for example, instead of converting an LTL formula to an automaton and having a planning process, instead you take a step and then use a reinforcement to modify your plan, right? Which one is more efficient?
Yes. So I didn't have time to go into that, but the conversion to a DFA is done only once. And the abstraction, the decomposition of the space, the properties of the robot was this other thing with which I did the cross product. So you don't need to recompute this, you don't need to redo this exponential, you just pay the cost once. It depends on the problem. If you're looking for policies, for example, as I did when I talked about uncertainty in the actions, it may be a good idea to compute all that beforehand. A thorough comparison is very, very difficult to do. I agree both approaches are interesting and both approaches need to be investigated. What one needs to decide is to what extent a policy is a good idea versus having a single plan.
I was wondering if you could talk about what you think might be the required replanning rates for the different components in that picture you drew.
This again depends on the kind of system that you have. What I can say is that motion planning algorithms have become so fast that yes, indeed, they can be used in a replanning loop. However, I think one has to also look at the kind of problem that you are solving. Maybe replanning is enough for you, but in some cases, replanning may not be enough because you may be doing you may be taking an action that cannot be reversed much, much later. And at that point, then I think it is worth paying the extra time for computing a policy that will get you out of difficult situations.
Thanks for the talk. Do you think that the task and motion planning problem is an interface problem of combining the two?
Can you keep the microphone close to you? I cannot hear you.
Sure. Do you think the task and motion planning problem is an interface problem of how to combine the existing algorithm of task planner and motion planner, or do you think that in order to solve the problem, we really need a brand new algorithm?
Mm-hmm. Yes. So far we've been combining things, but what I tried to say with this talk at the very end is that maybe we need to reconsider that. Maybe if we look at the problem as a whole, we'll come up with new techniques for solving the problem. But so far the combination has been very challenging.
Yeah. Thank you for the talk. Okay. Thanks. Thank you, ma'am, for the talk. I was wondering, how does the LTL specifications constraint-based planners scale up to constraints that are dynamically changing while the task is being performed?
Okay. This is something that is under investigation. It depends on how quickly you can. I don't know which of the two approaches. Probably we'll have to take that offline. I don't know which of the two approaches you are talking about, the LTL approach or the constraint satisfaction approach. But the issue is that when you, for the constraint satisfaction, it depends very much on how quickly you can modify the constraint that is solved by the LTL solver, the constraint satisfaction solver. We can use very, very powerful tools today. I'm just amazed at how big are the problems that can be solved in a relatively short amount of time. We are doing some experiments in that direction. Again, I don't have a definite answer on how far we can go, how fast this can be solved. But it's a very interesting point, what you're raising.
Thank you very much for this very interesting and very clever talk. I have just a short question. It's just asking your opinion, because I saw that you are starting to work with the robots that goes into contact and with the environment. So how do you think that force could be included as applying variable in your whole scheme?
Mm-hmm. Yes, I think that our planners should have the capabilities to deal with force. And I think we are very close I told you about we got constraints, probably we can get forces under control with the planning framework, and this will, I think, make things much easier for us when we try to combine, when we try to provide a planner as a module in a larger framework.
Okay, so let's thank Lydia again.
Thank you very much.